Okay, okay, so good afternoon, Charles. Uh, I think more people will join from the last class.
No, it's all right, Professor.
It's okay. Okay, so from I hope you up to date with the lectures from Professor Dilip Patil. In the week one, he did kind of introduction to commutative rings, ideals, prime ideals, maximal ideals, and some properties of them, based on which I did some mm, problems on the first tutorial class, and I did introduce algebraic sets and based on that Zariski topology. But today's class will be purely commutative algebra, because on week 2 he did modules over a commutative ring, and excuse me, okay, and algebras over a ring, again commutative, and so I hope you are already familiar with these terms, because in today's lecture we'll be doing some problems from both these modules and algebra.
Yes, I managed to go through some of the lectures,
Okay.
especially for the second week. Yes, I
Yeah.
had not started on week number 3 because I'm still working on the assignments. Uh, okay. Do you need them typed or we use our freehand?
Actually, that is not up to me. Uh, I think freehand would be fine. I'm not sure, but it would be better if you mail NPTL and confirm with them. But I personally think the typed would be very much, uh,
Better.
yeah, better,
Okay.
but it would be time consuming.
Yeah, because I was thinking of using LaTeX
Yeah, yeah.
to typeset the assignments. Yes, but it's not much anyway.
But if you at least don't have time to type, then write clearly. At least the terms and the calculations should be like proper, and should be.
Yeah, no, it's all right.
Yeah, yeah, yeah.
It's all right.
Okay, okay.
It's all right. And then, do you? Is there any provision to write after May?
After May.
For, yeah, because I don't foresee myself being ready for May.
Yeah, yeah. I mean, the gradings will be given after, I think, end sem. That is final exam. That is on April last week or May first week, I think. So
Okay,
you'll only be getting grades after that.
no, it's all right.
Okay, okay.
It's all right.
So yeah. Now, okay. So we'll be doing some problems based on modules and algebras. So
All right.
uh, let's not waste time and start. Uh, okay. So problems. One, that is, let R be a ring. Okay, so whenever I say ring, I mean commutative ring. With unity. With unity. So the first problem is let R be a ring. Now I define an R module M is said to be cyclic if it is generated by a single element. And it is said to be simple if AM has no R submodules other than 0 and M. So it is said to be cyclic when it is generated by a single element, that is, you can say M can be written in this form R dot A is from M, and said to be simple, that means it has no proper submodule other than the trivial ones, that is 0 and M. Now,
And M itself.
yeah, M itself the trivial submodule. Yeah.
Okay, okay.
So now my question is now is that, so that any cyclic R module is isomorphic to R by I for some ideal I of R. I is not mentioned, so you have to construct I. So that is the first question, and the second one is so that any simple R module is cyclic, and the third one is M is a simple module if and only if M is isomorphic to R by I for some maximal ideal I of R. So you can take your time and let me tell how to proceed for each of these problems. So I'll give you 5 minutes of time. Then,
Okay, it's all right. All right, let me just look
yeah.
into them. All right.
Yeah.
Yeah, I've just looked at the first part.
Hmm.
Uh, okay. I think we just have the key word there is the isomorphic there, which I think we should just look at the whether it is a surjection
Yeah.
or whether it is also injective. Uh, I'm not sure whether I also have to look at the word whether it is well defined somehow.
Yeah. So, one thing you said is true, is that there should be a surjective map. So, Uh, okay, we will go step by step. So, first,
Okay.
think about the evaluation map that is from. So, my question was that any cyclic R module is isomorphic to R by I for some ideal I of R. Now,
It's a question I do that one, isn't it?
sorry, yeah, Charles, you can say again.
Yeah, that question is it for module? Is it? I'm failing to. It's a question I do, isn't it? For R over I, R mod I.
Yeah, R by R mod I is a module.
Okay, it's fine.
So, okay, first clarify that. Now you see that uh, what are the elements of R mod I? That is A plus I, right? Where I is an ideal. Now,
And then that one is those are cosets.
yeah, and how do you define addition here? Uh, with A plus I plus B plus I goes to,
It's go to
yeah,
A plus B and
plus,
then plus I outside.
yeah. So that is, so from this one can say this is abelian group. You can uh, check the properties. Now how to define this scalar multiplication map, that is if your R is here and A plus I is here, then you see that it goes to uh, R dot A plus I, which is I'm defining this as RA plus I. So again you can check that this is this satisfies all the distributive properties and other properties that comes from module. So with this R by I is an R module. So now okay, we will come to our first question, that any cyclic R module is isomorphic to R by I for some ideal I of R. Now say R mod M is generated by M, that is M equals to R dot M. So now let my phi is a R to M, so module map where I is going to M. One can check that this is a module map, that is it is a abelian group, that is group homomorphism where phi dot R is phi R coming from R and A coming from again R. So obviously this map should be surjective because you see it should go to, and my aim is R dot M, so phi is surjective. And again, so this is a module map, so what you get car phi is a, I am writing this as I is a sum module of R. But you know that there is a 1-1 correspondence between ideals of R and submodules of R. Submodules of R module R. No, no.
Okay.
So this is like 1-1 correspondence between them, and uh, submodules of I mean, these are all well explained in the lectures of Professor Patil.
Yes.
Yeah. So
Mm-hmm.
you see that and from the uh, isomorphism formula that R by car phi should be image of phi, but this map being surjective, so this is M. And
Oh,
so
okay. That takes us to the isomorphism theorem.
oh, okay. So like in the group theory you have studied na that if uh, G, okay, I will write this as first isomorphism formula uh, for modules. So uh, let psi from R to R dash be a homomorphism of modules, then there exists an isomorphism R by car psi isomorphic to image of psi. So this is quite standard formula, and one can replicate this from the first isomorphism formula for groups or rings. Uh, so uh, Charles, I can give you a proof, but I think it will be better if you just uh, look at any standard book. You will see there, because we have to focus on the problems.
Yeah, no, it's all right, Professor.
Yeah, yeah. You can just
Yeah, no, it's all right.
yeah,
I'll check. I'll
and
check it later on.
if not,
All
if
right.
you are unable to find, you can just mail me, then we can discuss there. This is my mail address.
Yeah, no, it's all right.
Yeah, but for now the theorem is enough for now. So just my name and
Yeah, no, it's all
okay,
right.
okay, okay. So uh, okay, so from there you can see that this uh, what I was trying to prove, that uh, any cyclic R module is isomorphic to R by I for some ideal of R. So I is already a submodule of R, so that is ideal of R. So we have proved that M is isomorphic to R by I. This is first proof. Now for the second, uh, my proposition was any simple R module is cyclic. So this is kind of the bigger class cyclic R modules and simple R modules. Now how to prove this? This is quite trivial, because we know that simple modules only have trivial submodules. So let you take any non-zero element M of M. Now we know that any non-zero element, if it does not get annihilated with every element, but you know that any non-zero element from M will give you this R dot M is a uh, non-zero submodule of M. This is because 1 dot M, that is M, belongs to R dot M, right? So this is already non-zero, so my Rm is non-zero, but this is some module and m is simple, so only possibility is rm should be m. So we are done, right? That is the definition of uh, cyclic module.
Cyclic modules, yes.
Yeah. So the only non-trivial and interesting problem from this proposition uh, is that this one, that if m is simple R module, uh, m is simple R module if and only if m is isomorphic to R by I for some maximal ideal I of R. So from proposition one can see that the converse part, that is if m is isomorphic to R by I for some maximal ideal, then it is simple. So why this is quite relatively trivial, because you know that uh, so first we will do converse part. So let m is isomorphic to R by I is maximal ideal. Now uh, again we will use this correspondence, that ideal of R and uh, some modules of R modular. So you see that any proper sum module of m corresponds to a proper sum module of R by I, but proper sum module of R by I same as proper ideal in R by I, right? But I is a
Mm-hmm.
maximal ideal, so M has no proper sum module. That is
It means it's M itself.
only M. If you take here ideals, only two ideals are there, that is R and itself I. So if you take I
Mm-hmm.
in R by I, that is 0, so you would get 0 sum module there. And if you take R, that is R by I, so you would get M there. So M has only two trivial sum modules, so that is M is simple. Now again for the converse part you can go similar way, direct part. So suppose M is simple, but M is, if M is simple then M is cyclic, and if it is cyclic then it is isomorphic to R by I for some ideal. We don't know if I is maximal or not, but it is ideal. So at least we know that M is simple, so it is cyclic, so it is of the form R by I is an ideal. But now let's uh, M uh, say let's M is a maximal ideal that contains I, because you know that uh, where M is a maximal ideal. I I hope that you are already getting what I'm trying to say.
Yes,
That
yeah, I'm following.
yeah,
I'm
yeah.
following.
Yeah, okay. So then from isomorphism we would have a proper sum module in M, right? From this correspondence, that if it is proper ideal here, then we would get a proper sum module here, but contradiction, right?
Mm-hmm.
This would contradict to the fact that M is simple, so I is maximal ideal. So we are done.
Yeah.
So this problem actually ties so many ideas together, that is simple modules, uh, cyclic modules, and these with a prominent relation with maximal ideals. Later these will be helpful when I mean not in this course, but when you will learn classification problem for like semi simple decomposition, Jordan decomposition, like those things in semi
All
simple
right.
rings and modules. Okay.
All right. So, right, Prophet.
Okay, so the next one is uh, okay. So next one is a little constructive, but these are all important. So I guess we should do it. Let R be a ring that is commutative with unity, and let IR is an ideal. So again we know that an ideal is a module, uh, is an R module. So prove that I is a free R module. I guess you know what is a free R module. That is okay. I just write it down here. That is up to for isomorphic to Rn for n belongs to n. So Freer module, if and only if, that means it would have a basis like in linear algebra. If and only if I is principal, and by principal ideal I again write it is of the form uh, some A, and your A is coming from R.
Okay. Yeah. Yeah. Sometimes I confuse that one with the prime ideals, the principal one.
So principal ideal is means you know that elements can generate ideal, right? Like
Yeah, 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 yeah. So for prime, it is only generated by prime numbers.
not like that. Okay, suppose you say I have a ring Z. So say I take 6 from Z. Now you see that 6Z, which the elements are of the from 6, 12, 18. This
Yes, yes,
this is an ideal because it is a
yes.
abelian group. Also, it is closed under scalar multiplication with respect to Z.
Scalar multiplication, yes.
Yeah. So see that this is a principal ideal, but it is not prime because 2.3 is contained in here, but neither 2 or neither 3 is in here, right?
Yes.
So turns out there are principal ideals which are not prime. So now my proposition is that prove that I is a prior module if and only if I is a principal ideal
Okay.
uh, generated by a non-zero divisor. So what is a non-zero divisor? That means,
An integral domain.
I mean, an integral domain has all the non-zero elements which are non-zero divisor. But
Yes.
in a ring, there can be some elements which are again a zero divisor and again a non, again says Z6 where 0, 1, 2, 3, 4, 5. Here you can see that 1 is non-zero divisor, right? Because if you
Yes.
multiply with every non-zero element, it would be non-zero. But if you multiply 2.3 there, then it would be 0. Obviously, it should be mod 6. So 2 or 3 are both non-zero in Z6, but their product is 0 there, right? So
Yes.
yeah. So uh, by an I is pre-R module if and only if I is principal ideal and it is generated by a non-zero divisor. And from there one can show that R is a PID, that is principal ideal domain if and only if every ideal IR is free as an R module. So okay, first I will say that why 2 follows from 1. Now you already seeing that uh, I mean we are assuming that 1 is true. So if what is a PID, that is principal ideal domain, uh, that means it is an integral domain and every ideal is principal ideal, right? So already this is true,
Mm-hmm.
that I is a principal ideal generated by a non-zero divisor. So then every ideal is free, right? You are, so this is one liner. So I'll just write that 2 follows from 1. 2 follows from 1. Shall I write more? But I think this is enough.
Yeah, no, it's okay. I will check again on this.
Okay, okay. So, okay, so it is better to if I just prove 1, but I will give you 5 minutes to think about it. There is no point in rigorously me doing all these things. Just
All right.
try to think for 5 minutes and let me know.
Or for number two. All
No,
right.
2 is proved. So,
Okay.
question number
Number one.
2 and part 1. Okay, I'll be back.
It's all right.
So can anyone give me any hint or solution?
Okay, on the first part, I was just thinking of if you consider the basis, let's say 2 multiplied by z. So we'll see that each and every element could be written uniquely in form of the basis of 2 multiplied by something. So that's the condition that I realized that it could be a free Ara module. But then if it is a quotient now, to say, for example, if I can take maybe z divide by 6z,
Hmm.
and then I look at the elements inside, I don't think that one is a free module.
But okay. Mm. So first of all, that if I given that if you assume that I is pre-module, and here it again it is you have to prove that I is principal ideal. So then I think that it is important that you show that I is generated by only one element.
Hello.
Sorry.
Uh,
Yeah.
do
Oh,
like
yeah, I get what you're saying. Oh,
so?
so sorry.
Hello.
Yeah, Vaishnavi.
Yes. Do we need a non-zero divisor? Like it can be a zero divisor also. In that case, we will get I to be a zero ideal, right?
Yeah, yeah, it is given in the question. You see that if you look at the screen that I is a pre-module, uh, pre-R module if and only if I is principal ideal and generated by a non-zero divisor.
Okay.
Yeah, because if you don't assume that it is a non-zero divisor, then you cannot get the kernel zero, right? Or in your case, uh, I mean, if you get that I is generated by a single element, then you cannot say that it is linearly independent or not. Okay, I will go straight to the proof so that it will be easier. So suppose that I talk about the first converse, that suppose my I is a principal ideal and it is generated by a non-zero divisor. Suppose it's converse. Suppose I is generated by a single element and X is not a zero divisor. So now think of it as a module map from R to I as R going to R dot X, right? Module map, that is 1 going to X. Now what should be the kernel of F? That is R of R such that R dot X equals to 0. But your X is not a zero divisor, so only element there is 0, right? So what you are getting that R is isomorphic to I as an R module. So I think that that is, so I is a pre-R module. That is by definition, right? That I defined pre-module as some module which is isomorphic as module map to R to the power n. For n belongs to n, so one is a natural number. So converse what we are done. So for the direct part, suppose I is a free module. So let belongs to r to the power n, or n belongs to n, that is s phi is a basis of I, right? That means if the elements are of the form a1 up to an, you can write it as r of a1 direct sum up to r of an, right? Now if n is greater than 2, I mean take a1 and a2 from S and a1 dot a2 minus a2 dot a1 is 0, right? Since r is commutative. You can replicate this for up to n elements, right? Because you can take just I mean for 3 you can just write it a2 a3 dot a1 minus a1 a3 dot a2, and just put 2 here, and a1 a2 dot a3, and all this is possible because since r is commutative. So you can see that if you take these are coefficients, so you can see that these are all better to put it there, these are all linear combinations of a1 a2 and a1 a2 a3, so these are actually linearly dependent. So for n greater than equals to 2, we can always see that any two elements in I are linearly dependent, but our assumption is already that I is a free-R module, so only possibility, okay, I'll just write it here. So for a1 an I, for n greater than 2 equals to 2, they are always linearly dependent. So only possibility that I is isomorphic to R, that is I should be generated by a single element where A belongs to I. But if A is 0 divisor, then A dot R would be 0 for some R not non-zero. But this should then again that is phi R, phi of A R2I would have non-trivial kernel, contradicting R is isomorphic to I, so A is a non-zero divisor. So what we have proved is that this formula, this theorem, is it clear?
Yeah, yes, it is clear, Professor. I'm not sure on the other part.
Uh, okay, I have written explicitly everything, so you can again check back in your free time. I think recordings and
Yes,
the lecture notes should be available later. Okay.
done. It's all right. Thank you.
Okay, so now I'll be giving a question to you. I have done two rigorous proofs, so I think it's been some of you are already feeling bored or something. So maybe do this. Uh, try to produce some examples or proof or counter example. What I'm about to write. Let R be a ring M be a free R module. Give a proof or counter example to the following statements. Every spanning set for M over R contains a basis for M. And for the second, again these are all motivated from linear algebra. What is happening in mathematics is that uh, okay, first I write this independent subset of M over R can be extended to a basis for M. So what I was saying that what is happening in mathematics right now is like some great mathematician did some great stuff in linear algebra and topology and
In group theory.
in group theory and in differential geometry. Those are all basic subjects, right? So all we do in find new sets, new with new operations, and then try to replicate those results. So it is one of that
Or
kind of proposition that these are all true in linear algebra, right? Over a field, but what can you say about over a commutative ring with unity?
sorry, can you repeat that? I didn't get the question.
I mean, these two statements are
Mm-hmm.
true for linear algebra when your R is a field, right?
Mm-hmm.
But what can you
Yes.
say about when R is a commutative ring with unity?
Yeah. Yeah, that's a difficult one, Professor.
Yeah, it's not that difficult, but I mean, when you see it like this, but the example or the proof or in think when you will see, I think it will be interesting. Okay, let's try.
Yeah. All right.
So okay, okay, we'll
Spanning set.
So, in the first part, if we consider like Z as a Z module,
okay, okay,
like 2 and 3, the set 2, 3
yeah.
spans Z as a Z module.
Hmm.
Uh, mm,
But it is not a basis, right?
it's not base, it doesn't contain basis.
Be- uh,
Like,
uh, but what I mean, what are the basis for Z mod Z? I'm just asking.
that 1 minus 1,
Yeah, 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 yeah. So basis means both spanning and linearly independent. So 2 comma 3 spans Z, but it is not linearly independent, right? Because 3 dot 2 minus 2 dot 3 is 0. Yeah. So to record this answer, what uh, what Vijay just said, that is that consider M equals to R equals to Z. So 2 comma 3 spans Z as Z module. So, and there is another theorem that if you take for any R for n, there exists x1 to xr from Z, which spans Z, and this is minimal spanning set. That is the important part. But this will we can discuss later. So spans Z module because GCD of 2 comma 3 is 1, so we can write a dot 2 plus uh, b dot 3 as 1, right? Because GCD is the all uh, uh, of this form, na? This the least element in these linear combinations, because Z is a UFD, but those are all algebra 2 syllabus. so will not be talking about that here. So spans Z as Z module, but you can see that 2 dot 2 comma 3 is linearly independent. Sorry, linearly dependent. So it is not a basis. Remark, only two bases are basis of Z mod Z is R 1 and minus 1. Okay, so can you tell me about the second one? Again, you can think of Z mod Z and think about an ideal like 2 dot Z or 3 dot Z. 2 is linearly independent, right? But 2 cannot be extended to a basis, right? Because only bases are 1 and minus 1. So if you expand it to a spanning set, still you are not getting a basis. So Charles, you see that the counter examples are quite trivial yet interesting. So for 2 it is that take 2 is linearly independent, but it does not span Z as Z module because 2Z not equal to Z. Not isomorphic, not this is not equal to, because okay. So the next question is again interesting. These are all applications. I was trying to find more applications, but finding problems with and finding its solution is too much sometimes. Okay. Where Ni is to n a free Z module. So what I'm trying to say is that your Ni can be arbitrary, and so know that Z1 is singleton 0, Z2 consists of 2 elements, Z3. Again, you can take like infinite times Z2 direct sum of Z2. So Ni can be repeating or can be explicit. That does not matter for this question. So if it is free, then why? If it is not, then why not? Think. Should try to use whatever you have learned till now, and so for a free module there should be isomorphism from this module to a direct sum of some z power, so you can think from that too.
Hello.
Yeah. Okay. Yeah.
Uh, this is not free Z module because like you can consider the basis 1 0 0 0 0 1 0 0 like that. Like
And
and that will not be finite, right? Like for
finite means
um because like we should have a finite number of bases for this direct sum, infinite direct sum, right? Like to be a free module.
no, free module can be infinite dimensional also. I mean, if you take like this z to the power infinity or z to the power n, so this is free z module with infinite basis obviously, but this can be possible.
Okay.
But you already have taken the clue, that is you are picking basis, that is
Yes.
important. But now can you think of its order, like suppose your e1 is given, that is 1 0 0 0, and 1 is coming from zn1. Now what should be the order of e1? Order means if you add up to sometimes, then you will get 0. Means characteristic or something like
So that should be N1.
n1, right?
Yes, yes.
So it would have a image in, like if you uh, consider this as a free module, then it, from this it would have a map to some z to the power n or something. So it would have a image, right? But if that was isomorphism, then okay. As we are discussing, I think I should write this formally, because the notes will be available, so I have to write it formally. This is an order from NPTEL, so there is no escape actually. Suppose ZNI is a free module, then there would have been an isomorphism, that is from I equals to 1 to infinity ZNI to Z, say alpha. My alpha belongs to n. This is isomorphism. Now suppose then my e1 would go to phi e1 and it is non-zero, right? Now n1 dot e1 is 0, right? Because if you add it this e1 up to n1 times, you would get n1 better to write n1 dot 100, so n1 00, that is 0. So now phi of n1 dot e1 is n1 times phi of e1, right? Because these are z modules, so this is possible. So you are seeing that this is 0, but so that is order of phi of e1 is finite, but in a z module only finite order element in obviously it has to be free. uh, in a free z module in a free z module only finite order element is 0, right? Is this clear up to everyone? Because z is PID, and it is integral domain. So I mean, if you are say a1 dot a2 something and say n dot this is 0, then you are getting that n dot a1 equals to 0, n dot a2, and this. So this is only possible when your all individual entries are 0, right? So phi of e1 is 0, but e1 was your non-zero element and phi was isomorphism, so phi has to be bijective. So contradiction to the fact that phi is bijection. So direction I equals to 1 to infinity zni is not a free z module.
Okay. I've got a small question.
Yeah,
Uh, I also came across where it talks about torsion elements.
torsion elements, right?
Yes, I don't know how to relate to this one.
uh, for this case, I mean, this is not important. I mean,
Okay.
for our module am is said to be a torsion element if r dot m equals to 0 for some r non-zero and non-zero divisor in R. So it has to be non-zero. And
Right.
there is a theorem that if your R is PID, then any finitely generated module can be written as M, can be written as for any finitely generated R to the power n plus direct sum of torsion of n. This is all torsion elements. Sorry. But yeah, since you asked, I am only saying this, but this is not relevant to what I am doing right now. Okay.
All right.
I think we haven't done any algebra question yet. Only module questions we are doing. That okay. First try. First start with relatively trivial one. Question number it should be 5. Let phi of A to B be a surjective homomorphism of K algebras if B is a finite type K algebra then does this imply A is finite type? So you have to kind of give me a counter example or to prove this. So you can take some time and think about it.
Yeah, I'll take a guess.
Okay. Okay. Sorry. Yeah.
Yeah, I think it's also a finite type
Sorry.
because since this one is a surjection,
Yeah.
which means if I'm to create two sets there, and
Hmm.
each and every set will be, so I'll take some kind of the generators maybe
Yeah. Yeah.
in A, and then I create the images. I think each and every image will be meshed since it is a surjection there. I'm not sure whether we'll also proceed to find the kernel and what.
Yeah. I mean, mm, the answer to this question should be no. Uh,
I missed it.
but I was trying to find uh, where is your answer going wrong. But anyway, there is a very simple example that if you say take a map for to like up to infinity, and from there you have a map, and since the generators in this kx1 x2 up to infinity is, I can just map them to 0 and 1 to 1. So the phi is an algebra map, right? Phi is k algebra map. First we have to verify that, but this is, one can simply
Yeah.
verify that. Sorry.
Okay. My mistake was on taking the generators to be finite. I did not
Yeah,
take them to
yeah,
infinity.
infinite, yeah, yeah. Also,
All right.
if you are given a to b a k algebra map and your a is finite type, sorry, finite type, and this is surjective if given, this will imply that b is finite type. So if you are taking the domain finite type algebra, then codomain would be finite type, but the converse is not true, what we are seeing now. So this is different. So now your phi is a k algebra map, so and from here you can see that phi is surjective, and k as k algebra is finite type, but domain is not finite type. That means infinite type. So from here I can think of an interesting again question that that is often asked in interviews. uh, is every submodule uh, every submodule of a finitely generated module is finitely generated? Others can respond to me: Bijay, Vaishnavi, Namrata.
Okay, anything about A means if A is Noetherian, then it is, but in
Yeah,
general, it
uh, yeah, true if Noetherian. Finitely it R module. If Noetherian R module, what about general case? And if not true, then provide counter example. So no, Noetherian module, the concept of Noetherian module came from this only, that the the obstacle that every some module may not be finitely generated. So the answer is no. So what we have to find is counter example. Excuse me. Okay, try to find and I will come back in 2-3 minutes.
Yeah, I was looking at the set of integers.
So, can anyone provide me any counter example?
I was just comparing the set of integers and the set of even integers.
Okay.
But then I forgot this one. We are in the R module, but I'm not sure whether this can be, was looks this looks like there are Z modules. If I did not check on the R modules. It's,
Okay, so you are saying that Z is finitely generated
yes,
as,
by single
yeah, single
by the
element.
generating element one. Yes,
Yeah. But when you take 2, 4, 6, 8, this is an submodule
yeah, that's a submodule, yes,
of
of
Z.
even integers generated by two.
Yeah. But this is generated by 2.
Yes,
So this is finite, right?
yeah. If we assume that they are finite, yes,
So
and then
actually,
that would mean that if I'm to express them as a linear combination of that, they will be then our they have to be multiplied by one,
yeah.
which
And
gives us a contradiction.
yeah, and also Z is Noetherian as Z module. So anyway, every submodule in Z should be finitely generated, and also it is principal ideal domain, so it's generated by only single element. Also, every ideal should be free. I mean, there are like many things, but anyway, so now uh, think of this as module. Then you will see that your K is a field, suppose. Then you will see that this thing is generated by over same thing as uh, finally generated, right? Because it can be generated by 1, but x1, x2, x3 dot is not finitely generated as kx1, x2 module, right? Is this clear, or shall I explain it?
Yeah, it is clear on my part.
uh, Adarsh, Bijay, Vaishnavi?
Yes, it is clear.
Okay, okay, okay. uh, okay, let's do another problem. 6 should be 7. Let M be a finitely generated A module and phi from M to AN is a surjective homomorphism. Now, if phi of mi equals to ei for every I to n, then prove that m equals to m1 to mn square phi, and deduce that car phi is a finitely generated A submodule of M. So these are keywords R. This is. Can you think about this and tell me? Also, I will soon be exhausted of the problems. So let's take 5 minutes to think about this, and then I will discuss this. It will be the last problem for today.
It's all right.
So, the MIs are generators of module.
Sorry,
The MIs that M1 to MN, these are generators of the module. Is it given? I mean,
actually not.
so what are these? Means
So,
like,
I think these are uh, random elements which are being mapped to EIs. So
okay, synthetic surjective map. So the pre-image of
yeah,
EI,
yeah, yeah, yeah. Like
but
the choice of we made. So the pre-images may not be unique, but we are just picking out, and yeah.
If it is a surjective homomorphism,
Yeah,
M mod kernel phi is isomorphic to an
yeah,
to the n. So now since an is free
yeah,
and it is isomorphism, so EIs are the basis for an as an A module.
okay,
So image of means since it's isomorphism, I'm consider the inverse map an to M mod kernel phi
okay. You are saying that A mod kernel phi
isomorphic to an.
n. So this is free. So
Is
to EI,
EIs are
you are getting mi bar.
MI var. So EIs are generators. So the images of these generators has to be generators.
Yeah,
So MI bars generates M mod kernel phi as a M module,
yeah.
A module.
A module. Yeah.
So any representative of these
Okay.
MIs
Hmm.
uh, say means like and take any element of M
Hmm.
that is uh, written as a combinations of
These
MI bar
bars. Yeah.
and bar we can take common out that is a kernel phi part
Okay.
and the MIs are the generators. Is it okay? Means the generator says
Yeah. One
the
thing
MI any
is.
representative of these
Yeah.
concept.
Yeah. Yeah. So one thing you are saying that if you take m to m, so this would imply that m bar belongs to m by car phi. So then you can write it as m bar as ai mi, right? So
Yes,
one thing you can write it as m minus ai mi belongs to car phi, right? Because am bar minus ai mi,
AI MI bar is same as
you can just,
AI
yeah, you can take, just
the
put
same.
it, yeah, these are just abuse of notations, but yeah, should be 0 in m by car phi, right? From here you can just write it as m minus ai mi belongs to car phi. So from here, yeah, you can write it as car phi plus m1 to mn, right? So one thing is clear that car phi plus m1 to mn, this is contained in m, and also you have seen that m is contained in car phi plus m1 up to mn. So this would imply that m equals to car phi, but in the question I have given it should be a direction. So needed to show, can you say, tell me why it should be direction, Vijay? It should be this, right?
Yeah,
So uh, now again, if you check the map, initial map from A to An, you would see that this uh, I mean, if you take any element A from car phi and m1 up to mn, then you would see that phi of A should be 0 and phi of A, if your A is say BI then it would be going to BI right? Okay, I will be explicit. Summation of BI So it should be bi of phi of mi, and it should be bi ei, right? And an is free, so bi ei equals to 0 would imply that bi equals to 0 for all I.
So, our module was M mod kernel phi, that is isomorphic to AN,
Yeah,
and so mi bars are non-zero, right?
yeah,
These are generated of M mod kernel phi.
yeah.
That itself, that mi is not in kernel phi. So the intersection is empty. That
No, no,
mi
no,
bar.
no. From we are not using that argument. We are using that an is free, and this a has this representation because it is contained in this. So now phi of a should be 0 because this belongs to kernel phi, and phi of a should be biei. So that means biei is 0, but this is an element in an, and an is free, so each bi has to be 0, right? So this would imply that our uh, this element BIMI should be 0, right? Because MI bar 0 means MI belongs to car phi.
Mi bar are generators of M mod kernel phi.
They are not
These are
0.
zero.
Yes, you are
So
right.
that means mi doesn't belong to kernel phi for every I.
Yeah.
So
But
the
what about their linear combination?
yeah. So okay.
So that you see that what to show that their linear combination is not 0, then only we need this freeness, this freeness of an, right?
Yeah, true.
Yeah. Oh, okay. So uh, now going to the second one.
Hello.
Yeah.
Okay. So how you are saying
So,
MIs are non-zero?
uh,
It can
mi
be
is a
zero,
non-zero,
right?
we have taken that way. Okay, I should have written here. Uh, mi non-zero, and uh, I mean if mi is at 0, then it should be 0 map, right? Also, if one of the mi is 0, then it should not be a surjective map, right?
Yes.
Right?
Yeah.
Yeah. So I mean, from the conditions, it is enough if I don't write mi not equals to 0. Okay. So now for the second thing, that car phi is finitely generated. Uh, Now I will use this second isomorphism formula, that is uh, car phi of m1 up to mn by m1 up to mn. This is isomorphic to car phi of car phi intersection m1 up to mn, right? But from here we already know two things, that is this first sum in the left hand side and the denominator side, and that is m and m1 to mn should be isomorphic to car phi, and the this should be 0, so it should be car phi. Now quotient module of a finitely generated module is finitely generated, right? Because if you are given m by n, and if m is generated by say m1 to mk, then mi going to mi bar, these are the generators there. So question mark final is a finitely generated module, obviously over R. So car phi is finitely generated R module. Oh, A module, sorry. Okay. Okay, is this all right? Okay. Okay, thank you everyone for joining. Uh,
Thank you, Professor.
yeah.
Yeah, how can we get this presentation?
How can we? Okay, okay.
Uh,
So this
yeah,
is
would
called
you?
second isomorphism formula.
Yeah, we just wanted maybe this presentation maybe just to go through it again.
Yeah, yeah, I will go. So if we are given say m1 and m2 are two some modules of m, then m1 plus m2 by say m1 isomorphic to m2 intersection m1 intersection m2 as R module homomorphism. So again, I will not be proving this here, but you can just refer to any standard book, algebra book, like Damit Foot or Heisenberg. Think Atia already assumes all these things. So okay, okay. Is this okay?
Yeah, it is. Thank you very much, Professor.
Yeah, yeah. Thank you, thank you. We'll meet in the next class. Okay, okay. Bye, bye
All right.
everyone.
Thank you, Professor.
Bye.
Bye.
Thank
Thank
you.
you.
Thank you.